Hi everyone, we're starting our next lesson, which is on decomposing functions, and it's on section still 14D from the textbook. That's where you'll be getting your homework from. Okay, so what we're going to do right now is, before we get started on the decomposition of the functions, what I'd like to do is I would like to just take one example of the opening problems, and I'd like to go over it with you and give you an explanation overall, and then we'll move on to the decomposition of the functions. Okay, so we are given f of x is equal to 2x plus 1 over 3x minus 2, and we're told that g of x is equal to 5x minus 1. We are told to find f of g at 2 and f of g of x, g of f at 2, and g of f at x. Okay, so what I'm going to do is I'm just going to start by doing f of g at 2. So in doing f at g at 2, I'm just going to take the first one, f of g at 2. And essentially, there are two ways that I can go about doing this. Now, if I decide to insert first the value of the 2 inside of g of x, and then that answer will go into f of x, then I can do it that way. So essentially what I'm doing is I'm taking my g of x function, which is 5x minus 1, and I insert 5 times 2 minus 1, which gives me 9. So I know that when my value of the x going in the g of x function is 2, the value of the g of x, or the y, coming out is 9. So that essentially what it means is that when my value of the domain of 2 goes in, so my value of the domain, which is 2, goes in, the value of the range that comes out is going to be 9. Now that value of the range that we know to be 9 coming out of the g of x function, when I replace that now into the f of x function, then that becomes, it is no longer the range, but it becomes the domain of f of x. So that it's going to be 2 times 9 plus 1 all over 3 times 9 minus 2. And so that I end up getting 19 over 25. So that what this essentially means is that when my value of x is equal to 2, in the new f of g function, the value of the y coming out, or the value of the range, is going to be 19 over 25. Now that's the first way that we can do this problem. The second approach that we can take is that I can actually do f of g at x first, and then replace the 2 in afterwards. So this is the first method, method 1, and a second method we'll call method 2, so that I can just take the g of x function and replace it inside of the f of x. So if I do f followed by g, then I will have 2 times 5x minus 1 plus 1 all over 3 times 5x minus 1 minus 2. So what I have done is I have inserted the g of x function inside the f of x. So wherever there was an x in the f of x function, I replaced it with the g of x function, which is 5x minus 1. So if you take a look here above, I have taken the g of x, 5x minus 1, and I've replaced it inside of x here, in the f of x function, and in the denominator as well, 3x minus 2. So that when I get my solution here, I get 10x minus 2 plus 1 all over 15x minus 3 minus 2. That gives me a final answer of 10x minus 1 over 15x minus 5. So that's my f of g of x. If I now do f of g at 2, all I do is I replace the value of the x, which is 2, in for x in the composite function, so that it becomes 10 times 2 minus 1 all over 15 times 2 minus 5, which is equal to 20 minus 1, which is 19, and it still gives us over 25. Notice that we have exactly the same answer as in the previous one, in the previous section. The only difference being that I inserted one function inside another first, and then my final step was to insert the value of the domain x to get the corresponding value of the range y. In the first case, in method 1, what I did was I went through several steps. And so all I did was I said, I'm going to insert my domain of 2 into the g of x function first, and that range that comes out of there, which is 9 in that case, once it gets inserted into the f of x function, it becomes the domain of the next function to get then the corresponding value of the range of the combination of the two functions, which is still 19 over 25. Okay, so having said that, what I'd like to do is I would like to just again go over the concept of the definition of a composite function. So the composite function of f of g is written as f of g of x or f of g of x with parentheses. And the notation could be f follows g, or the composition of f and g. It doesn't matter, but f of g of x means that f follows g, etc. Okay, so when we're looking at f of g of x, for example, well, our input is the x value, and then the value that comes out of there, so it's a value of the domain, which is what I mentioned just a couple of minutes ago. The value of the domain going in, when it comes out of the first function, it is a value of the range, or the y. That value of the y then goes into the next function as a domain, or as a value of x, to then get its corresponding value of the range. So it's an input-output diagram that I have here. I input a value of x to get a corresponding value of y. That value of y in the next function becomes the value of x, which then, when it goes through the next function, it becomes the corresponding value of y again, or the range. Now, if we had to think of a composite function in a way that it could be applied to a real-life situation, so we're looking at a change in one quantity that produces a change in a second quantity, which in turn is going to produce a change in a third quantity. An example that I've always enjoyed looking at is the one on looking at communities, or looking at ecosystems, for example. So if you were in environmental science right now, you could be talking about this, and you would be really looking at a composite function, except you don't really realize that it's a composite function. And basically what it says is this: if we had, for example, a human population, a wolf population, and a rabbit population, for example. So the human population is going to affect the wolf population, which in turn affects the rabbit population. Now, as the human population is going to increases, the population of the wolves will decrease, because everyone, I think, pretty much knows that wolves do tend to avoid humans. And as a result of there being a decrease in the wolf population, that means that there's going to be an increase of the rabbit population, since rabbits are eaten by wolves. So I think it's pretty safe to assume that if we were to look at a new situation, such as if the human population decreased, what would happen to the rabbit population? So I think you should think about it for a second, but I think that it's quite evident that what would happen to the rabbit population is that it would also decrease. Because once the human population decreases, the wolf population increases, because there's less humans. And as a result of that, if there's a higher wolf population, that means that the rabbit population is going to have to decrease, because they eat them all up. Okay, having said that, let's look at very quickly the domain and range of a composite function. Okay, so the gist of it is this, that if I am looking at, now we have looked at finding the domain and range of all sorts of functions. So we looked at the domain and range of an actual graph. We've then looked at finding the domain and range algebraically, without the graph. Now what we're going to do is we're going to take a look very quickly at the domain and range of a composite function. Well, what if two functions are combined what is their domain and what is the range or the domain going to be of the new function? Okay, so if I've got this function right now that is, I've got to do k of h, okay, or it would be k of h of x. Okay, so those are the two options we have here. So if I were doing k of h, that means that the function, the h of x function, is going to be placed inside the k of x function, so that I'm going to be saying k of h is equal to the square root of 3x plus 12. Okay, so that is my new function, k of h. My k of h is the square root of 3x plus 12. Now, if I had to ask, what's the domain of this function? So my question is, what is the domain here? Well, we have to remember that what we're looking at is we're looking at restrictions. And we know that one of the things that the value of x is not allowed to be is it's not allowed to be a negative number under a square root sign. So that I would automatically take what's under the square root sign, 3x plus 12, and I would set it greater than or equal to 0, so that I would end up with 3x being greater than or equal to negative 12, so that 3x would be greater than or equal to negative 4. Oops, x would be greater than or equal to negative 4. So that we have the domain equaling x is such that x is an element of R. Again, we know that we don't have to put that x as an element of R, where x must be greater than or equal to negative 4. Okay, now, having said that, we have now to find the range. So we know that in order for this function to work, our values of the x are going to have to be greater than or equal to negative 4. Now, in order to find the range, however, well, the range depends on what our values of the domain are. So if I have a restriction on the domain that tells me that the domain has to be greater than or equal to negative 4, does it not make sense for us to go back to the original function of k of h of x, so k of h of x, okay, and say, well, what if I replace the value of negative 4? So if I do 3 times negative 4, that would be my first value that it is allowed to be, is negative 4, because then any number smaller than that is not going to work. So from negative 4 onwards, you are allowed to put that number in, so that I can say, well, then I've got 12, negative 12 plus 12, and we end up getting the square root of 0, which equals 0. Okay, so that tells me that when my value of x going in the function is negative 4, the value of y coming out, or the value of the range coming out, is 0. So that means automatically that my range is going to have to be y is such that y is an element of R, where the smallest value of y has to be greater than or equal to 0, because it definitely cannot be less than 0, because we're not allowed to have a 0, a negative number under the square root sign. So all I did was basically, I took my value of the domain where it started, and I inserted it back into the composite function to get what the value of the range would start at, and the value of the range would start at 0. And if you actually graphed this, okay, so if we actually graphed this, oops, what you would see is that the graph looks approximately like this. So this is just an approximation, but it would look something like that. So that my values of the x, and it would start at negative 4. So my values of x would start at negative 4, but my values of the y are going to be above 0. So that means above the x line, or the x-axis. So that it would be 0 or greater. The graph will never go below the x-axis. Okay, so moving on, we're just going to do very quickly a decomposition. Now, decomposing functions is really the opposite of the composition of the functions. So when we decompose f of g of x, we're bringing it back to the original f of x and g of x functions before they were combined. So it's similar to like when we expand and factorize binomials. They're opposite operations. Okay? So first we created composite functions, we combined them to create a new one. Now we have the combined new one, and we're going backwards, and we're going to try to figure out what were the two original functions before they were combined and placed together. Okay, so let's start by looking at an example like this. Okay, so I've got f of x is equal to the square root of 2x plus 1. Now, looking at the order of operations, if I had to replace f at 2, that means that replacing f at 2 means that I would first replace the 2 underneath the square root sign, which gives me 5. And then from there, the next operation would definitely be that I take the square root. So the operation that's completed first is going to be under the square root sign, and then I take the square root in the end. Now, if we were going to look at this from another point of view, let's take a look at a couple of different solutions that we have here. Okay, so what they've basically told you in the problem here is, it says, in each of the problems below for a given function h of x, so h of x is your composed function. So it's the one that is already combined. They've called it h of x. And h of x is equal to f of g of x. So f of g of x means that g of x has been placed inside of f of x. So if we are given h of x, the combination, being equal to the square root of x squared plus 1, it means that g of x is the first operation that's going to be occurring, that's going to be inserted inside of f of x. So technically, the first operation that's occurring is x squared plus 1. So I could say that g of x is equal to x squared plus 1. And because that g of x is being inserted inside of f of x, that means that f of x is going to have to be the square root of x. Because this, I'm just going to circle this, because the g of x, or x squared plus 1, is going to be inserted inside root of x to give us the root of x squared plus 1. Now, that is one solution. There are other alternatives as well. There's also another possible solution. There's usually more than one correct answer in decomposing functions. It isn't always necessarily just one answer, but it can be more than one. So in this case, we have also another solution. I could have called the g of x x squared, and I could have called f of x x plus the square root of x plus 1. And that means that g of x would have been inserted inside of f of x, and it would have still given us the square root of x squared plus 1. All right, so that's one example. Let's take a look at another example. So another example is where we are finding two possible decompositions. So two possible decompositions. Let's look at one of them. One possible decomposition here. One possible decomposition would be that since I'm doing f of g of x, that means that my g of x is going to be inserted inside of f of x. So I'm pretty sure I'm going to say that g of x is going to be equal to here in 1 over the x cubed plus x plus 1 all squared. I'm pretty certain that I'm going to be saying that g of x is equal to x cubed plus x plus 1. That's the one that pops into my mind immediately. So that if g of x is equal to x cubed plus x plus 1, then f of x would have to equal 1 over x squared, because the x cubed plus x plus 1 has to be inserted in there to give us the final product of the h of x function. Now the alternative way of looking at this, and this is an easier form, is that I could have said g of x, and this is kind of taking the easy way out, but I could have said g of x was equal to x cubed plus x plus 1, and I could have said squared, and that would have meant that f of x was equal to 1 over x. Like I said, this technically looks like it could work for any type of question. I just make something worth x, and then the other one just goes to the other function. Okay, So that's another example. Now I have a third example here that the answer is already up here, but if I've got h of x and I'm doing f of g of x, again, so the g of x is going to be inserted into f of x, which means that my g of x, it looks like, is going to be x minus 3, and therefore f of x is going to be x cubed plus 2x squared plus 1. Okay. That pretty much covers, let's actually do one more example. Let's take a look at this example here. So I've got h of x is equal to f of g of x, which is equal to 3x squared. So they want you to find f of x and g of x. So g of x is occurring before f of x, so it's going to be inserted. So that means that I'm going to make my g of x, I'm definitely going to make my g of x equal to x squared, which automatically tells me that my f of x is going to have to be 3 raised to the power of x. Okay. Next one. I'm going to leave a couple of questions for you to do in the video now, so I will give you a couple of spots where you're going to give me the solutions to these. And your homework will be for you to complete exercise 14D, number 3, 4, and 6. And there's a handout on Google Drive, which is called, I believe it's called Composing and Decomposing Functions. Okay, I'll see you next time.